Preface to Report of Airship Hindenburg Accident Investigation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to learn how to volunteer, please visit LibriVox.org. Recording by Scott Danneker, Elizabeth City, North Carolina. www.zeppelfart.com. U.S. Department of Commerce Air Commerce Bulletin, Volume 9, Number 2. Preface to Report of Airship Hindenburg Accident Investigation. In an order dated May 7, 1937, made by the Secretary of Commerce pursuant to the Air Commerce Act of 1926 as amended, relating to the investigation of accidents in civil air navigation in the United States, South Trimble, Jr., Solicitor, Major R. W. Schroeder, Assistant Director of the Bureau of Air Commerce, and Dennis Mulligan, Chief, Regulation and Enforcement Divisions of the Bureau of Air Commerce, all of the Department of Commerce, were designated to investigate the facts, conditions, and circumstances of the accident involving the airship Hindenburg, which occurred on May 6, 1937, at the Naval Air Station, Lakehurst, New Jersey, and to make a report thereon. Commander Charles E. Rosendahl, United States Navy, Colonel C. DeForest Chandler, United States Army, Colonel Rush B. Lincoln, United States Army, Colonel Harold E. Hartney, Technical Advisor to the United States Senate Committee on Commerce, the Honorable Gil Rob Wilson, Director of Aeronautics for the State of New Jersey, and the Honorable Grover Loening, Aeronautical Advisor to the United States Maritime Commission, were designated as technical advisors. General Lieutenant Friedrich von Böttischer, German military attaché, was selected by the German ambassador at the invitation of the Secretary of Commerce as an observer at the investigation. On the fourth day of the hearings, the members of the German Commission appointed to investigate the accident, including Dr. Hugo Eckener, Lieutenant Colonel Joachim Breithaupt, Professor Günther Bach, Professor Max Diekmann, Director Dr. Ludwig Dürr, and Staff Engineer Friedrich Hoffmann, appeared and thereafter acted as observers and testified as witnesses. The United States Navy Board of Inquiry was represented throughout the hearing by an observer. When the accident occurred, an aeronautical inspector of the Department of Commerce was present. Before midnight of the same day, other representatives of the department reached the scene of the accident. After a preliminary inspection had been made, public hearings were held from May 10th to May 28th in the main hangar at the Naval Air Station, Lakehurst, New Jersey, in Asbury Park, New Jersey, and in New York City. In addition to that provided by the department's representatives, assistance was received from the United States Navy Department, Bureau of Investigation, Department of Justice, Weather Bureau, Department of Agriculture, National Bureau of Standards, Department of Commerce, New York City Police Department, and the Bureau of Explosives. Aviation companies, newspapermen, newsreel representatives, and photographers, many of whom were eyewitnesses to the event, and others, furnished valuable information. End of preface. Part 1 of Report of Airship Hindenburg Accident Investigation by the United States Department of Commerce. This is a LibriVox recording. All LibriVox recordings are in the public domain. Part 1. Introduction. Note: all times reported herein, unless otherwise indicated, are Eastern Standard Time, EST. The airship Hindenburg was destroyed by fire at 6:25 p.m. Eastern Standard Time, May 6, 1937, at the Naval Air Station, Lakehurst, New Jersey. Schedule. The airship was completing its first scheduled demonstration flight for the 1937 season between Frankfurt, Germany, and Lakehurst. It had departed from Frankfurt about 8:15 p.m. GMT on Monday, May 3rd, and was due at Lakehurst on the morning of Thursday, May 6th. It was due out of Lakehurst at 10 p.m. Eastern Standard Time that night. Because of unfavorable winds encountered en route, its arrival at Lakehurst was deferred until 6 p.m. Thursday evening, and departure was to be postponed until midnight or later in order to resurface and prepare for the return voyage. Ownership and operation. The ship was owned and operated by the Deutsche Zeppelin Reederei GmbH of Berlin, W8, unter den Linden, Germany. The flight, which was to have been one of a series to be made into United States territory during 1937, was authorized by a provisional air navigation permit from the Secretary of Commerce and a revocable permit issued by the Secretary of the Navy to the American Zeppelin Transport, Incorporated, of 354 4th Avenue, New York City, as General United States Agent of the Deutsche Zeppelin Reederei GmbH for the use of the landing field and facilities at the Naval Air Station at Lakehurst. Certificate of Airworthiness. In March of 1937, the German government renewed the airworthiness certification of the aircraft, reporting that all of its safety devices had been inspected and found satisfactory. Crew. According to the crew list, see Appendix 1, furnished by the American Zeppelin Transport, Incorporated, the personnel on board, including officers, numbered 61, of whom 22 died as a result of the accident. Passengers. The passenger list, see Appendix 2, likewise furnished, shows that 36 persons beside the crew were on board. Of these, 13 died as a result of the accident. Other passengers and members of the crew sustained serious injuries. Goods carried. Total weight of the freight carried was 325 pounds. The freight was stowed in the main freight compartment at frame 125. 2 dogs were kennelled at frame 92, and 3 packages were stowed in the control car. Mail was carried in a compartment on top of the control car. Of the freight and mail, only a few pieces of mail were recovered. Ground crew and facilities. The ground personnel consisted of 92 Navy personnel and 139 civilians. Practically all of the ground crew had previous experience in landing airships. One member of the ground crew died as a result of burns received during the accident. Flight across the Atlantic. Across the Atlantic from Germany to the United States, the flight had been uneventful, save for retarding winds, which were not unusually turbulent. The route traversed by the ship on this side of the ocean was from Nova Scotia via Boston, Providence, Long Island Sound, New York, and thence to Lakehurst. After passing over Lakehurst the first time, it proceeded to cruise along the coast for a few hours before retracing its course from Tuckerton, New Jersey, to the Naval Air Station. End of Part 1. Part 2 of Report of Airship Hindenburg Accident Investigation by the United States Department of Commerce. This is a LibriVox recording. All LibriVox recordings are in the public domain. Part 2. The Airship. Design and Construction. The airship was placed in service early in 1936. It bore builder's number LZ-129 and had been constructed by the Luftschiffbau Zeppelin of Friedrichshafen, Germany, an organization which had previously built 118 Zeppelin-type airships. Briefly described, this type of design provides for a framework of duralumin metal girders with tension wires. There is division by frame wirings of the body into different compartments into which the gas bags are placed to receive the lifting gas, a keel walkway to take certain loads, a framework with an outer cover of fabric to give form, and engine cars suspended from the frame outside the ship. The Hindenburg was a Zeppelin-type airship, having an axial corridor constructed longitudinally through the center of the hull. 1936 record. During its 9 months of operation in 1936, this airship made more than 55 flights, flown 2,764 hours, cruised 191,583 miles, crossed the ocean 34 times, carried 2,798 passengers, and more than 377,000 pounds of mail and freight, all without mishap. Dimensions, capacities, other characteristics. Its length was about 803.8 feet, height 147 feet, maximum diameter 135 feet, fineness ratio, length over diameter, about 6, total gas volume 7,063,000 cubic feet, normal volume 6,710,000 cubic feet. Weight of ship with necessary equipment and fuel was 430,950 pounds. Maximum fuel capacity 143,650 pounds. Total payload 41,990 pounds, and total lift under standard conditions was 472,940 pounds. Its rated cruising speed was about 75 statute miles per hour. Its maximum speed was slightly over 84 miles per hour. Passenger space was entirely within the hull. Controls. The control system was the conventional Zeppelin-type control with two rudders acting as a unit for horizontal control and two elevators acting likewise for vertical control. Emergency elevator and rudder control wheels were installed in the stern of the ship. An electrical gyroscopic device attached to the forward rudder wheel provided automatic steering. Outer cover. The outer cover consisted of cotton fabric on certain parts of the frame, on others linen, and depending on the stresses to which it was exposed. The exterior surface of such fabric was treated with several coats of Ceylon and a mixture containing aluminum powder. As protection against ultraviolet rays, the inner surface of the fabric on the upper part of the ship was coated with red paint. Gas cells. In each of the 16 compartments of the ship was a gas cell containing the lifting gas, hydrogen. The middle cells were separate, whereas the two bow and the two stern cells were intercommunicating. The gas cell material consisted of a film placed between two layers of fabric. Nettings were provided to prevent all sharp edges from damaging the gas cells. It was stated that the amount of gas leakage through this fabric approximated a maximum diffusion rate of about 1 liter per square meter per 24 hours. Gas valves. 14 automatic and an equal number of manually operated or maneuvering valves were affixed to the cells. A single maneuvering valve was affixed to cells number 1 and 2 and cells 15 and 16. Gas could be released from the cells by manual operation of the valve controls located in the control car and hooked up with the valves by a series of wires and pulleys. This was done under the supervision of the captain or the watch officer in charge. The automatic or emergency valves were provided to reduce the pressure of the gas in the cells under certain circumstances. The cells were numbered from stern to bow, from 1 to 16. The maneuvering valves of cells number 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, and 14 were connected to a master wheel in the control car, which operated all of them as a unit. And there also were independent controls for the separate maneuvering valves so that the gas in them could be released as desired. Cell fullness or pressure indicator. Electrically actuated gas fullness or pressure units were connected to the gas cells to indicate visually by sensitive meters in the control car the pressure and hence the relative fullness of the gas in the cells. These units were located in the ship's axle corridor or walkway. The accuracy or sensitivity of this system was not definitely established. An appreciable amount of gas might have been able to escape before such escape would show on the visual indicator unless that indicator was kept under close observation. According to witness Hugo Eckener, a cell could lose at least 200 to 300 cubic meters of gas before the indicator would show such a loss. Such an amount is only a very small proportion of a cell's content. Gas shafts. Between every two cells, a gas shaft was provided into which gas could be valved directly from the cells. The shafts extended vertically from the lower walkway through the axle walkway to the top of the ship for ventilation purposes. On the top, they came in contact with the outside air under the protection of specially designed gas hoods or ventilators. Propulsion. 4 Daimler-Benz diesel engines, type LOF-6, each having a maximum rating of 1,100 horsepower, were used to propel the airship. They were contained in 4 outside engine cars, or gondolas, and were suspended laterally on the ship's hull by struts. Engine room telegraphs provided communications between the control room and the individual engine cars. The fuel used by the engines was a diesel oil. Propellers. The 4-bladed propellers attached to each engine were of wood and 19 feet 9 inches in diameter. The blades were armored with brass sheathing about 1½ inches in width on the leading edge from about the 43-inch radius to the tip of the blade. The sheathing was bonded to the ship's structure through the engine. Tests were made with the prototype of the propellers used on the ship. They were tested to loads 50% in excess of the thrust to which the propellers would be subjected at takeoff, which was 3 times greater than the thrust which would be imposed at cruising speed. They also successfully withstood the block tests. They were limited to 1,400 revolutions per minute in forward rotation and 1,120 revolutions per minute in reverse rotation. These revolutions were below the fluttering speeds of the blades. Electrical power plant and installations. The electrical power plant of the ship consisted of 2 50-horsepower diesel-driven generators with switchboard and distribution system. These generators were independent of the outside propelling engines. The electric generators and principal members of the system were located amidships on the port side of the keel. Current was generated for the purpose of lighting, cooking, radio, and steering. There were 2 circuits, one of 220 volts, the other of 24 volts. The ship's electric wiring was of copper and was installed in accordance with the rigid regulations governing the German mining societies. The lead to the stern light, which was on a 220-volt circuit, using a very heavy cable protected by a special fuse, extended from the electrical power plant along the lower walkway and thence to the light. No electric wiring extended above the equator except in the extreme nose of the ship. Ropes and cables. The main mooring steel cable was fixed to the tip or nose end of the ship. The port and starboard bow trail ropes were attached to the ship at frame 244.5. These trail ropes were about 413 feet in length. It is understood that in landing the ship, it was the practice to approach the ground mast from leeward and drop the wire cable and the 2 trail ropes. The main cable was then coupled to a mooring mast cable leading through the top of the mast. By means of a winch, The cable was then reeled in, pulling the mooring cone on the ship's nose into the corresponding cup on top of the mast. The trail ropes were coupled to ground ropes and led out to the sides to keep the ship headed into the wind and towards the mast and to prevent it from overriding the mast structure. In the stern, at frame 47, an after-mooring cable was in practice let out through a metal fairlead. At frame 62, a port and starboard spider was let out at landing. Besides those enumerated, the ship was provided with other mooring or landing tackle for such use as circumstances warranted. Ballast arrangements. Water was generally used for ballast. The emergency ballast was contained in fabric containers, 4 of which, of 500 kilograms of water, were suspended in the bow and an equal number in the stern. To the right and left of the lower walkway were suspended a number of other ballast tanks, some of 2,500 liters each and others of 2,000 liters each. The ballast tanks could be emptied partially or totally by the elevator man by means of control wires connected to a ballast stand in the control room. Several of the fuel tanks could also be used for ballast purposes. Radio equipment. The radio room was located above the after end of the control car. Its equipment provided for two-way radio telephone and telegraph communications. It included a short-wave and a long-wave transmitter, each with 200-watt antenna capacity, 2 all-wave receivers, and 2 direction finders. The frequency of the short-wave transmitter was 4,160 to 17,500 kilocycles. The frequency of the long-wave transmitter was 120 to 500 kilocycles. The frequency range of the receivers was 12 to 20,000 kilocycles. Power for the transmitters was obtained from a 220-volt direct current supply generated by the ship's electric power plant. The receivers obtained their high voltage from batteries, and power for their filaments was obtained through a series resistor from the 24-volt ship's generator. For the short-wave transmitter, there was a trailing antenna of 26 meters length. For the long-wave transmitter, a trailing antenna of about 90 meters length was used. These trailing antennas were located directly below the transmitters and ran through an aperture in the keel of the ship. There was a fixed antenna extending from the control car about 15 meters towards the stern. The fixed antenna was used only for receiving purposes. In addition to this equipment, there was located in the bow an emergency transmitter and receiver, current for which was obtained from a generator driven by pedal power. This emergency set employed a trailing antenna about 20 meters in length. Lifting gas. The ship was inflated with hydrogen. According to the evidence adduced, this gas has the following characteristics. It is colorless, odorless, and tends to diffuse in all directions. The only way that hydrogen could be detected by smell would be due to the presence of impurities as a result of the process by which it was produced, or contamination from some source, such as rubberized fabric. Hydrogen, for lifting purposes, has a density of approximately 5 pounds per 1,000 cubic feet, depending on the temperature and pressure. Its lifting power is the difference between the density of air and its own density. The density of air is about 75 pounds per 1,000 cubic feet. Assuming pure hydrogen, its lifting power would therefore be about 70 pounds per 1,000 cubic feet. An opinion was advanced that the general order of pressure of the gas within the cells of the ship was somewhere between ½ inch and 1 inch of water pressure. It was stated that the density of hydrogen corresponds to air at a temperature of 5,000 degrees Fahrenheit, and that the chimney effect of its escape through the gas shafts of the ship was so very great that there was no possibility of its moving down the shafts into the lower parts of the ship. The flammable limits of a mixture of hydrogen and air are probably between 4.5% and 62% of hydrogen. Other experiments have shown variances from 8 through 9.8% to 66%. The temperature at which chemical activity between hydrogen and oxygen takes place is between 507 degrees to 557 degrees centigrade. This temperature range is dependent upon the amount of hydrogen present. The range of activity of combustion will be from the lower limit of 4.5%, at which there will probably be an invisible union without evidence of flame. A combustible mixture would be more hazardous in an atmospheric condition of 98% relative humidity and temperature 60 degrees Fahrenheit than in dry air with relatively low humidity, since dry hydrooxygen is more difficult to ignite and its ignition temperature is higher. In an explosion, the flame propagates in all directions in the combustible range between 15 to 45% of hydrogen. These figures were arrived at experimentally with glass or metallic apparatus which did not have effect upon the combustion temperature. Catalytic metals, having absorption properties, would be likely to affect the combustion at lower temperatures. Finished duralumin would not be expected to have material catalytic effect upon hydrogen. Bonding. The whole metallic structure of the craft was bonded. End of part 2. Part 3 of the report of the Airship Hindenburg accident investigation by the United States Department of Commerce. This is a LibriVox recording. All LibriVox recordings are in the public domain. Part 3. The landing maneuver. Meteorological conditions. With respect to the meteorological conditions in which the landing was conducted, a summary of the general weather is given, as well as the local conditions prevailing at Lakehurst at the time of the accident. General. The 7:30 a.m. Eastern Standard Time United States Weather Bureau map of the vicinity, including the northeastern tier of states, shows a disturbance over central New York and northeastern Pennsylvania, with a cold front extending from this center southwestward to West Virginia. This front separated neutralized polar air to the east of the cold front, which had become warmer and more moist, and neutralized colder air to the west of the front. The warmer and more moist mass of air covered the middle Atlantic states, southeastern New York, and southern New England. The cold front advanced eastward during the day from central Pennsylvania at a rate of 12 to 15 miles per hour, passing Lakehurst shortly after 3:30 p.m. There was not quite sufficient surface heating during the early afternoon to set off a thunderstorm at Lakehurst, and it was not until the front passed and some slight lifting of the air mass occurred that a thunderstorm began. The records of the Naval Air Station show that the thunderstorm began at 3:40 p.m. and ended at 4:45 p.m. Telegraphic reports indicate the thunderstorms in and to the west of New Jersey were not severe, nor were they of a well-defined squall character. Between 12 p.m. and 1:30 p.m. Eastern Standard Time, these storms extended in a definite belt over the region of Harrisburg, Pennsylvania, northeastward to Bear Mountain, New York, and New Hackensack, New York. Between 1:30 and 2:40 p.m., none was reported. Between 2:40 and 3:40 p.m., Camden and Fort Monmouth, New Jersey, only reported thunderstorms. Between 3:30 and 4:30 p.m., Lakehurst, Mitchell Field, New York, and Floyd Bennett Field, New York, reported them. Between 4:40 and 5:40 p.m., none was reported, and between 5:40 and 6:40 p.m., Floyd Bennett only reported one. Summarized, the thunderstorms in eastern New Jersey were of a local character and not severe. The New York Weather Bureau Office Bulletin, issued at 1:20 p.m. May 6th, follows. 1800 GCT. Moderate wind shift with increasing and lowering clouds. Possible thunder showers, New York and vicinity, expected in middle or late afternoon. Stop. New York. Scattered cumulus and small cumulonimbus approaching from west. Visibility excellent. Surface wind south, 12 miles. Barometer 29.68, falling steadily. Temperature 66. Local. With the passage of the front at Lakehurst, the wind shifted to the northwest with gusts up to 20 knots, and was accompanied by slight increase in barometric pressure, decrease in temperature, heavy showers, and several thunder showers. Then there followed a rapid decrease in the velocity of the wind, and its direction became variable. The wind at Lakehurst at 6:10 p.m. went into the southeast and remained there for about 45 minutes, shifting again, and then it became mostly southerly. The front, after passing about 3:30 p.m. EST, apparently slowed down to a rate of approximately 7 miles an hour and was in the vicinity of Atlantic City, New Jersey, at 8 p.m., its direction being north-northeast through southwest, clearing rapidly after 8 p.m. During the afternoon, cumulonimbus and cumulus clouds developed locally, and with the approach of the front, there appeared a well-defined mild squall line in the west, which moved slowly over Lakehurst and apparently became stationary between it and the shoreline until about 5:30 p.m., when it continued eastward. Several heavy showers occurred between 5 and 6 p.m., with accompanying thunder. Visibility was reduced during these showers. At 5:12 p.m., the thunderstorm then over the field was moving north, and it was believed that by the time the ship arrived at the station, the storm would have moved away from the station. The ship at this time was out of sight because of low visibility, and the ceiling, in the direction from which it was expected to approach, was not more than 500 to 600 feet. Conditions at the time of approach were: ceiling between 2,000 to 3,000 feet, clouds, 0.7 stratus, very light rainfall, sky showed signs of clearing to the westward, barometric pressure 29.72, temperature 60 degrees Fahrenheit, relative humidity 98, surface wind light, variable, and shifting, and at the precise moment of the beginning of the landing was about southeast 1 knot. It was expected that the surface wind direction would go into the west, or perhaps the northwest. Reports from Trenton and Camden, New Jersey, indicated that the wind was westerly and that at Camden was about 18 knots just previous to the landing of the ship. Wind at the top of the weather tower on the field was west, 6 knots. The approach level of the ship was about 200 feet above the ground. The top of the tower is 186 feet above sea level. Ground elevation at place of landing was about 90 feet above sea level. The inversion condition was 60 degrees at the lower level, 59 at the second, and 57 at the third level, being temperature readings at various levels from the top to the bottom of the weather tower. As the ship was approaching the landing area, occasional lightning was visible from the distant south and southwest, but none was observed over the field at this time. When the headway of the ship was stopped, a pronounced shift of wind was felt on top of the mooring mast, from southerly to southeast or south-southeast. This wind was colder than the previous wind had been. Communications. Radio. Regular reports from the ship were received as scheduled at the Naval Air Station, Lakehurst. At one stage in the latter part of the flight, the static was bad, but it did not prevent communications between the ship and ground stations. Shortly before arrival at Lakehurst, direct communication was maintained by the ship with the Naval Air Station. At 1:55 p.m. Eastern Standard Time, the station received a message from the commander of the ship stating that he would depart from Lakehurst as soon as possible after arrival. At 4:42 p.m., the commander of the station radioed the ship. Conditions still unsettled. Recommend delay landing until further word from station. Advise your decision. At 4:52 p.m., the commander of the ship replied,
"We will wait till you report that landing conditions are better.
At 5:12 p.m., the commander of the station advised the ship.
Conditions now considered suitable for landing. Ground crew is ready. Period thunderstorms over station. Ceiling 2,000 feet. Visibility 5 miles to westward. Surface temperature 60. Surface wind west-southwest 8 knots. Gusts to 20 knots. Surface pressure 29.68.
At 5:22 p.m., station commander radioed ship.
Recommend landing now.
At 6 p.m., station transmitted to ship.
Overcast, moderate rain. Diminishing lightning in west. Ceiling 2,000 feet. Improving visibility. Surface wind west-southwest 4 knots. Gusts under 10 knots. Surface temperature 61. Pressure 2970.
At 6:08 p.m., station commander sent last message.
Conditions definitely improved. Recommend earliest possible landing.
This was acknowledged by the ship. Prior to the accident, all of the ship's trailing antennas had been reeled in. No high-frequency transmissions were being conducted when the trail ropes were dropped from the ship. Both transmitters were turned to the off position at that time and remained so thereafter. The radio dynamotors had also been shut off. The last message transmitted over the ship's radio was shortly after the landing signal had been sounded, about 15 minutes before the fire. It was sent on the long-wave transmitter to Lakehurst at 6:10 p.m. Eastern Standard Time. During the landing, watch was kept on the long-wave receiver. No landing report was transmitted from the ship to Germany while it was over the field at Lakehurst. One of the ship's radio men stated that atmospheric disturbances had been encountered during the afternoon of May 6th, but that such conditions improved toward evening and continued to improve during the last 30 minutes of the flight. No difficulty was experienced during that period in sending or receiving, either on the short or long-wave transmitters or receivers. Witness Herbert Dova, ship radio operator, stated that he was on watch and actually listening to the radio until the fire started, and that he did not notice any interference which could have been caused by improper bonding or shielding, and that he did not receive any interference such as might have been transmitted by local station. There was no oral communication between persons in the ship and on the ground during the maneuver. The sequence of actions in bringing the ship up to the landing point is in part revealed pictorially by the track of the ship over Lakehurst, drawn on a map of the Naval Air Station, with notes on the maneuver by witness H. W. Bauer. Among other data, the map provides information respecting successive altitudes, speed, operation of engines, release of ballast, and valving of gas. Operation of engines. About 10 minutes before dropping the bow trail ropes, the engines were running full cruising speed ahead, the ship's speed about 33 meters per second, or approximately 73 miles per hour. The altitude of the ship, according to its altimeter, was then about 180 meters, or 590 feet. About 8 to 9 minutes prior to the release of the ropes, all engines were idled ahead, altitude 150 meters, or 492 feet, ship speed falling off to 15 meters per second, approximately 33 miles per hour. Then, in fairly rapid order, the after engines were idled astern and then put full astern to reduce the speed to 12 to 13 meters per second, approximately 27 miles per hour, after which all engines were idled astern. Altitude at this time was 120 meters, or 393 feet. About 2 minutes prior to dropping of the bow trail ropes, all engines were put full astern for a period of about 1 minute to stop the ship, after which the forward engines were idled ahead and the after engines were idled astern. When the trail ropes had been dropped, the forward engines were given a short burst ahead, then idled ahead. Release of ballast. Starting at a point about 3/4 of a mile from the landing point, 300 kilograms, or 661 pounds, of water ballast was dropped from ballast bag at frame 77. Then, in rapid order, from the same frame, at about intervals of 1,000 feet, ballast was dropped twice again. The second time 300 kilograms, 661 pounds, the third 500 kilograms, or 1,100 pounds. This release of 1,100 kilograms, 2,420 pounds of water ballast took place within a period of 2 to 3 minutes before the trail ropes were dropped. Valving of gas. According to witness H. W. Bauer's sketch, gas was valved on the wheel for 15 seconds, approximately 10 minutes before dropping the bow trail ropes, the ship proceeding at full cruising speed. About 8 minutes prior to dropping of ropes, gas in cells 11 to 16, first 5 forward cells, was valved for 15 seconds, ship then proceeding at 15 meters per second, or approximately 35 miles per hour. Approximately 4 to 6 minutes before dropping the ropes, gas in cells 11 to 16 was again valved for 15 seconds. Speed of the ship 12 to 13 meters per second, approximately 27 miles per hour. About 2 minutes prior to dropping of ropes, gas in cells 11 to 16 was valved for 5 seconds. Crew as ballast. According to the elevator man who had taken over the elevator helm in the landing approach, the ship was still slightly tail heavy after dropping water and valving gas. Consequently, 6 men of the crew were sent forward to the bow in order to equalize the weights. He was unable to account for the tail heaviness of the ship, after the ballast had been dropped. Tail heaviness. The ship was weighed off to the west of the field and was found a little light. There followed the trimming operations that have been described in the preceding paragraphs. There is evidence to show that the tail of the ship was heavy during the maneuver. Witness Albert Zamt, second in command of the ship, accounted for this condition by saying that it was due to the consumption of fuel, that it gave him no concern because it was very little. There was diversity of opinion advanced regarding this condition of the ship. Witnesses H. W. Bauer and C. E. Rosendahl considered it to be normal. The latter stated that the ship's tail heaviness had been logically accounted for. Under the circumstances in which it landed in a light wind with little airflow on the tail surfaces and consequently little aerodynamic lift, 120 pounds midway from the tail of the ship would be felt by the elevator man and be noticed by those in the control car who were watching the inclinometer for that very thing. That the condition did not exist from the time of the dropping of the bow trail ropes during the 4 minutes intervening before the fire broke out. To other witnesses the ship appeared heavy in the stern. Among them witness Benjamin May, in charge on top of the mooring mast, and W. A. Buckley, assistant mooring officer. Witness Hugo Eckener indicated, according to his information, that while the ship may have remained in satisfactory trim from the time the trail ropes were dropped until it burned, such interval was a short period of time. He did not think that a hydrogen leak would have been so large that in such a relatively short time it could have been noticed. He mentions the testimony of witness H. W. Bauer relating to the trimming operations, in which a very short time before the accident 6 men had been ordered forward. From this he infers that shortly before the ship reached the landing position it was necessary to trim the ship by putting weight forward, and that the elevator man could hardly have noticed anything during this interval because the ship had no more forward speed. He further stated that careful calculations showed that the trimming moment affected by these operations amounted to at least 70,000 to 80,000 meter kilograms, or 506,391 to 578,933 foot-pounds of trimming effect. When this effect is compared with a trimming moment that could be obtained aerodynamically at full cruising speed by the use of the elevator controls, in the order of 150,000 to 200,000 meter kilograms, or 1,085,124 to 1,446,820 foot-pounds, then it became clear to him that the ship was very badly out of trim. Witness Eckener also testified that witnesses in the control car had reported that the out-of-trim condition originated approximately 1/2 hour before the landing maneuver after going through the rain clouds, that the ship became tail-heavy by running through heavy rain because the weight of the rain is greater in its effect on the horizontal fins, which are behind the center of gravity. There is also another apparent effect of rain upon the ship. That is, the tail would seem to be heavy to the elevator man while the ship was running through rain, because it automatically has a tendency to nose up, since the center of aerodynamic pressure moves aft. This effect, however, disappears very rapidly after passing through rain, and in the present instance must have disappeared quickly because the ship as a whole was light. The ship, 10 minutes after passing through heavy rain clouds, should have again been in good trim. In the opinion of witness Eckener, however, it appeared so tail-heavy that it became necessary to apply a trimming effect of some 70,000 meter kilograms, or 506,391 foot-pounds. Furthermore, he indicated that if the ship had been as tail-heavy before it proceeded through the rain clouds, it would not have been operated without the release of ballast. As no testimony was given that the ballast had been dropped before the ship moved into the rain clouds, witness Eckener believed that some unusual condition in the ship might have developed prior to the ship's landing. With regard to the amount of rain that the ship had been exposed to during the landing maneuver, there appears to be some difference of opinion. Witness Zompt stated that there was a little rain as the ship crossed the field at the beginning of the maneuver, not heavy enough to weigh the ship down as much as 500 kilograms, or 1,100 pounds. That was the only rain experienced during the last 2 hours of the flight, because they had avoided the rain carried in the weather front. As the ship took a final bearing on the field, it made a wide turn into quiet weather, returning to the field in this condition. According to him, the front had passed and the weather was favorable for landing. The sky was overcast, but without disturbances or squalls. Witness Nelson Morris, a passenger, stated that a very light rain fell exactly as the ship came over the field the last time, but until that time there had been no rain. Witness Anton Wittemann, who had commanded the airship Graf Zeppelin, stated that when the Hindenburg approached for its landing maneuver, and as it passed through the front, the weather conditions as seen from the ship were entirely favorable. The thunderstorm had passed into ordinary rain. The ship entered somewhat heavy rain, which became much lighter when closing in on the station. At the approach there were no cumulus clouds. There was a clear-cut stratus layer from which light rain was falling. Witness H. W. Bauer, second watch officer of the ship, said that about 20 minutes before the landing approach the ship passed through a heavy rain and through stratus clouds containing rain before making the approach. It did not pass near any lightning. Altitudes at landing. When the ship was brought to a stop over the landing point, its altitude was about 180 feet above the ground. It rose to about 200 feet when the bow port landing ropes checked its further upward rise. Thereafter, it descended to about 135 to 150 feet when the accident happened. Electric installations. According to witness Philip Lentz, chief electrician of the ship, no fuses blew, nor did any circuit breakers operate just prior to the fire. The several circuits of the ship were intact. The interior ship lights and navigation lights were burning as usual. Rudder. Two witnesses testified that the top and bottom rudder did not appear to be working in unison when the ship came over the field. From other testimony, it appears that the rudders were functioning normally. End of Part 3. Part 4 of the report of the Airship Hindenburg accident investigation by the United States Department of Commerce. This is a LibriVox recording. All LibriVox recordings are in the public domain. Part 4. The Fire. Ground log. It was the practice at the Naval Air Station to maintain a log of events in connection with the landing of the Hindenburg. The log of its last landing reveals that the first approach of the ship in landing maneuver was sighted at 6:15 p.m. Eastern Standard Time, May 6th, approximately over the officers' quarters on the station. At 6:21 p.m., the bow trail ropes were dropped on a bearing of 30 degrees from the mooring mast. First the starboard rope, followed immediately by the port rope. Ship was first observed afire at 6:25 p.m. Description of landing. The landing made on this occasion has been described as a high landing or flying mooring, a method of landing which is occasionally employed. Some qualified witnesses stated that it was normally conducted in every respect. Among these were witnesses Rosendahl and A. F. Heinen. Others indicated that the approach seemed hurried, that the ship made what seemed to be a fairly short turn and approached the mooring circle fairly rapidly. Based on the statements of other witnesses, Witness Eckener expressed the view that the ship must have proceeded in a sharp turn to approach for its landing. Witness Zampt said the turns were normal. Incidents before the fire. Before the fire broke out, the ship was being held by the bow port trail rope, which had been coupled to the port yaw line, and a strain had been taken on this rope around the niggerhead of the ground winch. The bow starboard trail rope had not been coupled to the ground line, but was being handled by the starboard bow landing party. At no time during the approach did the ship come closer to the mooring mast than 700 feet. The main bow cable of the ship at this time had been let out about 50 feet, but neither it nor any of the cables or ropes in the stern had reached the ground before the fire started. After the trail ropes in the bow had been dropped, the ship no longer had any forward speed. It began to move up and astern, and also to swing slowly to starboard. Then a light gust was felt from port. Fluttering of outer cover. Witness R. H. Ward, in charge of the port bow landing party, a couple of seconds before the fire, had his attention attracted by a noticeable fluttering of the outer cover on the top port side between frames 62 and 77, which includes cell number 5. No smoke or other disturbance accompanied the flutter when he first saw it. It was a wave motion. In his opinion, the motion of the surface was not due to the slipstream or resonance effect of the propeller. It was entirely too high from the propeller. It appeared to him to be more like an action of gas inside pushing up, as if gas was escaping. He apparently had seen this action occur in other aircraft. The ship had no perceptible forward motion the time he observed the flutter. Its engines were idling in forward rotation. The fabric did not open up when he first made the observation. The flutter was followed by a ball of flame approximately 10 feet or so in diameter. Then came an explosion. On a diagram, this witness indicated that the first appearance of fire was near the top of the ship and above the point where he saw the flutter. With respect to this testimony, witness Eckner said that a leak in a gas cell, permitting the escape of 40 to 50 cubic meters of gas per second, would be sufficient to cause a flutter in the outer cover which could be observed as reported, but probably would not be enough to draw the attention of those in the control car to a loss of buoyancy aft. Witness R.W. Antrim, who was on top of the mooring mast, also stated that he saw that the fabric behind the after port engine was very loose and fluttering. It extended rearward and upward from the after port engine to a quarter of the way to the tail. Strain on the port trail rope. The drift of the ship to starboard, according to the mooring officer, witness Tyler, was finally checked by means of the port trail rope. This rope was hauled up taut on the winch. The starboard trail rope was being handled by the manpower of the starboard bow party. Witness Albert Stuffler, one of the ship's cooks, who was looking down from a window in the ship, stated that he saw how
the landing crew came running up, and how they loosened the knot of that rope and fastened it to the lower lines on the ground. Then I saw how the ropes took tension, and at the moment I felt a very strong detonation of the ship, a vibration of the ship. I did not notice any explosion. I only noticed that vibration I was speaking about before.
He thought the ship was striking the mooring mast. Witness H.W. Bauer stated that after the landing rope had been fastened, he went from his position to the port window in the control car and observed the tensioning of the landing ropes. At the time of that observation, there was a strong shock in the control car, and his first assumption was that the landing rope had broken. Witness Max Zabel, ship's third officer, stated that he observed the bow trail ropes being dropped, that the port trail rope became rather tight. He saw the ends of the rope, which were tied together, whirl around and tighten. Immediately after this landing rope had become tight, an explosion was heard and the destruction of the ship occurred. He described the vibration that was felt in the control car as an extraordinary one. Witness Dova, ship's radio man, testified that while watching one of the landing ropes being handled by the ground crew, there suddenly was some tearing in the ship, a metallic tearing. A passenger reported,
And then, as the rope was getting taut, I heard a detonation.
Sensations within the ship. In describing their nervous reactions at the beginning of the accident, some of the persons within the ship, in addition to such descriptions as are provided in the preceding paragraph, spoke in effect as follows. Witness Severine Klein. When the ship was almost standing still, it gave a sudden jolt. Witness Xavier Meyer. First he heard detonation, then he noticed the vibration, the shock, and fell on his back. Witness Heinrich Kubis. First heard or felt an explosion approximately at the time that the ship took a sharp inclination. Witness Lentz. The sound that he heard he thought might have been a landing rope breaking. Witness Klaus Hinkelbein. The jerk and the sound of the detonation and the sight of the fire or the reflection of the fire were all simultaneous. Witness Kurt Bauer. Noticed a crackling shock which originated in the rear. Witness Wittemann. When he heard dull detonation, thud, his first idea was that a rope had parted. Witness Walter Ziegler. Saw how the port landing rope was hauled tight. Shortly thereafter he heard a dull thud or detonation, and a heavy shock went through the ship. Witness Kurt Schönherr. It was a strong shock he sensed after hearing a rather dull detonation. Witness Samt. His first intimation that something was out of order was a heavy push. About the same shock as if the ship had been pushed to the side and the landing rope had broken. Neither prior to nor after the push did he hear a muffled explosion. He did not associate the push with anything that might have occurred in the after part of the ship. Appearance of fire. Numerous expert and lay witnesses on the field testified as to where they first observed the fire on the ship. And there was great diversity in this testimony for reasons that are very apparent. Among the most important of these reasons were the extreme rapidity with which the fire spread, the different positions of the witnesses with respect to the ship, the size of the ship, more than 1/6 of a mile in length and an overall height equivalent to a 12-story building, and the fact that at the time of the fire it was still daylight. It is estimated that the interval between the first glimpse of flame and the impact of the main body of the ship with the ground was 32 seconds. The great majority of the ground witnesses who testified as to the first appearance of fire were looking at the port side of the ship. After carefully weighing the oral evidence and transcribing to a master diagram the numerous diagrams on which the ground witnesses indicated their first observation of fire, we conclude that the first open flame produced by the burning of the ship's hydrogen appeared on the top of the ship forward of the entering edge of the vertical fin over cells 4 and 5. The first open flame that was seen at that place was followed, after a very brief interval, by a burst of flaming hydrogen between the equator and the top of the ship. The fire spread in all directions, moving progressively forward at high velocity with a succession of mild explosions. As the stern quarter became enveloped, the ship lost buoyancy and cracked at about 1/4 of the distance from the rear end. The forward part assumed a bow-up attitude, the rear appearing to remain level. At the same time, the ship was settling to the ground at a moderate rate of descent. Whereas there was a definite detonation after flame was first observed on the ship, we believe that the phenomenon was initially a rapid burning or combustion, not an explosion. From the observations made, it appears that there was a quantity of free hydrogen present in the after part of the ship when the fire originated. A brief resume of the observations made within the stern of the ship shows that witness Helmut Loy, who was standing on the ladder leading up to the lower catwalk from the lower vertical fin and was looking up facing the port side of the fin, heard above him a muffled detonation and saw from the starboard side, down inside the gas cell, a bright reflection on the front bulkhead of cell number 4. He saw no fire at first, but a bright reflection through the inside of the cell. The cell suddenly disappeared because of the heat. Then cells 3 and 5 caught fire. This witness said he did not see the center of the origin of the fire, but it must have been further up, since he saw the reflection of fire through the cell wall material. It was the same type of explosion that one hears when using a kitchen gas range, when first lighting the flame or turning it off. Witness Loy did not smell any hydrogen at the time he made these observations. Witness Hans Freund was letting out the after mooring cable at frame 47 and had let out a few meters of it when he heard a muffled detonation. Fire was simultaneous with the explosion. He was surrounded by fire immediately. Witness Rudolf Sauter, who was stationed in the keel of the lower vertical fin, first heard a dull detonation, then saw fire in cell number 4, a big fire, which he identified as a hydrogen fire. None of these witnesses in the stern of the ship felt any unusual vibration or heard any breaking of structures prior to the detonation or the sight of fire or reflection of fire. None of the other members of the crew or passengers on board the ship observed fire or reflection of fire until after feeling an unusual vibration or shock or hearing the detonation. End of part 4. The report of the Airship Hindenburg accident investigation by the United States Department of Commerce. This is a LibriVox recording. All LibriVox recordings are in the public domain. Part 5. The combustible mixture and its ignition. Having retraced the course of events and circumstances surrounding the accident, we come to the question, why did the fire occur? As yet, with a few exceptions to be noted, no more has been provided than a hypothetical approach to the answer. We have weighed the several theories that have been advanced. Sabotage. The possibility that the cause is to be explained by premeditated or willful act has received active attention. Sabotage has been examined under 2 classifications. The first, external, including the use of incendiary bullet, high-powered electric ray, and the dropping of an igniting composition upon the ship from an aeroplane. The second classification, internal, including the placing within the ship of a bomb or other infernal device. To date, there is no evidence to indicate that sabotage produced the grim result. Accidental causes. In a consideration of accidental causes, two factors must be found together. There must be present a combustible mixture of hydrogen and oxygen of the air, and b, sufficient heat to ignite such mixture. In the analysis of the evidence, the mixture and its ignition are treated separately. Presence of combustible mixture of hydrogen and air. Accumulation through diffusion or osmosis. While it is conceded that the fabric of which the cells were made is slightly permeable to the diffusion of the contained hydrogen, it is not our opinion that this characteristic of the cell walls, under the circumstances prevailing, would account for a combustible accumulation of gas and air within the ship, the normal rate of seepage being, as was indicated under description of the cells, about 1 liter per square meter per 24 hours. Failure of valve mechanism. According to the testimony, only one valve failure had occurred on the ship. This happened when the ship was new. As a consequence, certain changes had been made in the construction of the mechanism. In any event, the failure noted occurred to an automatic or pressure relief valve which would not have been functioning at the time of this accident. However, because the valves were mechanical devices, it was possible that there might have been a defect or failure in them, but no testimony appears to show that this possibility was a likely one. Decreased ventilation. Another query regarding the presence of such mixture presented itself. Could it have been due to the reduced scavenging of the gas by the ship's ventilation system during the last minutes of the craft's existence, when its speed eventually had been reduced to a full stop, combined with the last valving operation about 6 minutes before the fire? This theory seems improbable, because of what was said about the efficiency of the ventilation system, and because of the fact that the chimney effect created by the 6-knot wind that was blowing at the ship's elevation during the last 4 minutes prior to the fire should have evacuated practically all of the gas from the shafts. The forward speed of the ship, reported to have been from 15 to 20 miles per hour, when the last valving operation was performed, should have been ample, it was stated, to have cleared the gas rapidly from the ship. A further argument made with regard to the scavenging of gas was that immediately after the last reported valving, the ship's engines were backed down hard, and that this deceleration should have tended to move the gas in the ship toward the bow and out through the forward gas shafts. In considering the production of such mixture by the rupture of a cell or cells, there are at least several avenues to explore. Entry of piece of propeller. One of these might have been laid to the failure of a propeller and the throwing of one of its fragments through the adjacent part of the hull into a cell. To this possibility there was devoted an extensive examination by experts of our staff and those of other agencies. The condition of the propeller of engine car No. 2 attracted our attention. Witness F. W. Caldwell, one of the country's foremost propeller experts was quite certain that the propeller of the after-port engine did not break in flight, but was shattered at the time the car struck the ground. He said that there was no indication of the separation of the sheathing from the blades except as the result of shattering on impact. Witness Deutsche, machinist in the after-port engine car, indicated that the propeller of his car was still rotating when it struck the ground, that he did not feel any unusual vibration of the engine before the crash. Fracture of hull wire. One other significant possibility must be discussed while the question of cell rupture is being examined. It was suggested that, while in flight, a tension wire might have ripped a hole in a cell and thus permitted a quantity of gas to escape. Coupled to this possibility is the testimony of witness R. H. Ward, digested briefly in the statement of facts, that he saw a fluttering in the outer cover above the equator between rings 62 and 77, and believed that this fluttering was caused by gas escaping into the space between the adjoining cell and the outer cover. A shear wire in one of the panels at the place from which the gas was escaping could have snapped while the ship was turning during the landing maneuver. Witness Ekener stated that such turns generate high stress in the after part of the ship, especially in the center section close to the stabilizing fins, which are braced by shear wires. The gas thus accumulated between the cells in the outer cover must have been a rich mixture. Such a mixture, enclosed in a space between the outer cover and the gas cells, would, if ignited, burn with relatively slow speed until gas in greater volume was released by the burning through of the cell walls. Witness Rosendahl recalled that in the early years of operation with naval aircraft, shear wires had broken with varying effect, causing no serious damage, however. Major structural failure. Consideration has been given to the possibility that a major structural failure in the stern of the ship caused the hydrogen to be liberated by rupturing a cell and forcefully breaking an electric lead or metal part, thus producing a spark. The fire broke out when the port trail rope, which held the ship to the ground, became taut. It was reported by some persons that at or about the time they observed the fire, they heard a cracking sound from the stern of the ship. An examination of the wreckage disclosed that the rivets, by which the after end of the axle corridor was connected through a fitting to the hull, had pulled out, that all of the radial wires in the small frame nearest the stern had broken in tension, that only a few of the small tabs of metal from the periphery of the frame, which had been pulled off the bight formed where the radial wires hooked onto the frame, were found on the ground below where the frame struck. The shearing of the rivets and the condition of the wire in the frame might be explained by the force with which the rear end hit the ground, or by the torsional or other stresses which the tail suffered in its last moments in the air. It has also been pointed out that the ship was stressed for greater loads than the tensional strength of the bow trail rope, and that the rope had not parted. Furthermore, it was observed that the eye through which the trail rope was attached to the ship and the longitudinal member to which the eye was affixed were intact after the accident. The 4 members of the crew in the stern of the ship testified that they did not hear or see any such structural failure prior to the fire. Ignition of the mixture. Many of the theoretic aspects of the ignition of the combustible mixture were dealt with at great length by a number of experts. Only a summary of this phase of the investigation is related in this report. Mechanical. If there had been enough heat generated by the friction of wires or other members of the ship coming forcibly into contact with each other, due to structural failure or breaking, a sufficiently hot spark might have been produced to set off such mixture. There is insufficient evidence to sustain a conclusion based upon this theory. Chemical. As has been stated, there are metals which have a catalytic effect upon a mixture of hydrogen and air and would materially lower its ordinary ignition temperature. But it does not appear that any such metal was in that part of the ship where the fire was first observed. Under the title of chemical possibilities, there has also been suggested that a flame might have been produced by spontaneous combustion. The evidence is inadequate to support this theory. Thermodynamic. In the examination of thermodynamic possibilities, much time at the outset of the investigation was given to the possibility of such mixture being ignited by the sparks from the engine exhausts. It was suggested that sparks or larger particles of carbon thrown out from the diesel engines might have been carried into the openings in the lower part of the hull or have been blown over the exterior of the stern and there have ignited such mixture. While the circulation of the exhaust gases set up by the direction of rotation of the propellers just before the accident, the after engines idling in reverse and the forward engines idling ahead, was different from that produced while under way, it was maintained by the German experts that this circumstance would not result in sparks or carbon particles reaching the interior of the hull, and furthermore that the sparks would not have been able to ignite such mixture on the top of the ship at least 165 feet away from the after exhaust outlets. Witness Ludwig Durr testified that very extensive experiments respecting this possibility had been conducted by the builders, and the results had been reassuring. When the engines are delivering 1100 to 1200 horsepower, the temperature leaving the piston before it enters the exhaust stack is 500 to 530 degrees centigrade. The temperature of the exhaust is lower. The engines ordinarily develop 800 to 850 horsepower. At this output, the temperature of the exhaust gases is 450 degrees to 480 degrees back of the cylinder. With a mixture of air sucked in, the temperature is reduced to 230 degrees to 250 degrees centigrade. Visible sparks have a temperature over 500 degrees centigrade, but lose their heat rapidly as they are impelled through the air. Had this been the cause of the ignition, it is believed that it would have come into play before the elapse of the 4-minute interval between the dropping of the trail ropes and the accident. That the heat of the exhaust gases caused the havoc is also improbable. If ignition had happened at the exhaust, it would have been necessary that the temperature of the band of air between the outlets and the place of the first flame would have had to be about 507 degrees centigrade. According to witness Durr, The temperature at the exhaust outlets was much lower than 507 degrees centigrade. With the Hindenburg and the Graf Zeppelin, no difficulties had been experienced from this quarter. Electrical. Under the classification of electrical sources of ignition, several were considered. A combustible mixture of air and hydrogen could have been ignited by the overheating of wires carrying current within the ship, e.g., by short circuit. Barring the possibility previously alluded to of a substantial failure in the stern structure of the ship, which might have produced a sudden breaking of such wires in the aft end of the ship, it is thought to have been only remotely possible that the mixture was fired by a defect or failure of the ship's electrical wiring. According to witness Lentz, who was stationed in the electrical power plant at the time of the accident and had most of the ship's electric indicators, fuses, and circuit breakers under observation, the various circuits were functioning normally just prior to the conflagration. No fuse blew or circuit breakers operated at that time. It was also observed that the cable carrying the current to the stern light was very sturdy and was installed so as to provide plenty of slack to compensate for expansion and contraction of the frame of the ship. Spark in gas fullness or pressure indicator. A theory introduced by witness Heinen was that the cause of the fire was due to the ignition of such mixture in one of the gas fullness or pressure electric meter actuating units fixed to the axle corridor in the vicinity of cells number 4 and number 5. He believed that a small pocket of gas accumulated in the folds or ridges of the cells surrounding the corridor and found its way into the inner recesses of the meter and was there ignited by an electric spark. That the fire thus created traveled up along the radial wires to the space between the cells and the outer cover, igniting the free hydrogen collected along the longitudinals at the top of the ship on the inner surfaces of the outer cover. That the relatively slow burning of such free hydrogen would account for the peculiar manifestations of illumination described by certain witnesses. That the fire in the second sequence then destroyed gas cell number 4, as seen by witness Loy. With regard to the presence of gas in one of the meters, it was estimated that in 1 hour the seepage in the axle corridor would have amounted to 1/40th of 1% of the volume of the corridor. That even in the motionless condition of the ship, the corridor would have been well ventilated due to the chimney effect created by a wind of 6 knots blowing over the gas shafts. That the ventilation in the corridor would have prevented pockets of hydrogen from forming because the air current through the corridor was not laminated but was made up of whirls and eddies. However, if it could be shown that a rent occurred in a cell below the axle corridor, then it is possible that some free hydrogen might have found its way into one of the meters. In regard to the ignition of such mixture within a gas pressure or fullness meter, the following is quoted from a report of the Bureau of Standards relating to Exhibit 74, one of the meters taken from the ship.
It is evidently intended for measuring and giving a remote indication of small gas pressures by electrical means. The gas pressure acts on a diaphragm in opposition to to a helical spring. A plunger attached to the diaphragm carries a coil of wire which has a resistance of 100 ohms. Two rollers connected in parallel make contact with the sides of the coil. Two flexible connections run to the ends of the coil. The change in the relative resistance of the two parts of the circuit between the contact rollers and the ends can cause suitable electrical indicating instruments in the control cabin to indicate the position of the coil and diaphragm and hence the pressure. All electrical parts are enclosed in a cylindrical metal box. The only openings into this box are 1. The hole, 10 millimeters in diameter at the top, through which the operating rod passes with a clearance of not over 0.05 millimeters, and 2. The opening at the bottom, which is completely filled by the 3-conductor cable covered with metallic braid, which connects to the rest of the circuit. The conical housing surrounding the metal box is well ventilated. The device seems to be excellently designed and constructed from the standpoint of safety, and there appears no way by which it could with any reasonable probability have caused a fire. An overheating of the device by short circuit seems impossible. A short circuit external to the device would impose on it only the full voltage, 24 volts, of the circuit and produce a rate of heat dissipation of less than 6 watts. A short circuit inside the device would not draw more than the 1 milliampere fixed by the external instruments. A simultaneous short circuit, both inside and out, would blow a fuse, if one was present, before a dangerous temperature was reached. Good practice requires such fuses on all such circuits, and one was probably used. The normal operation of the device should produce no sparks. Deterioration of the contact rollers or of the coil, or a breaking of a wire inside the metal box might produce a spark inside. It seems impossible that hydrogen should be present inside, as it could get there only by diffusion down the narrow clearance between the operating rod and its guide tube, 50 millimeters long. A spark could be produced outside the box only by the breaking of the 3-conductor cable. This cable is strengthened by the metallic braid and runs in a protected location along the structural member. It could not be determined whether or not the cable was definitely anchored to the member, nor whether the metallic braid was originally clamped to the metal box because of damage in the fire.
In the light of all the available evidence on this point, we believe that the possibility of igniting such mixture by the means just described was very slight. Resonance effect. High-frequency inductance. An attempt was made to discover if the ignition of such mixture could have been laid to spark emission due to resonance effect upon metal parts of the ship's interior caused by received radio waves of high frequency. There was on the field at Lakehurst a localizer beam radio transmitter of low power, maintained by an airline company, the on-course portion of which was so situated as to pass through the space occupied by the ship at the time it took fire. This transmitter was at that time about 1,800 feet from the ship. Its power output was 15 watts, its frequency 278 kilocycles. The maximum field strength authorized for this type of station is 1,500 microvolts per meter at 1 mile, which represents 15 ten-thousandths of 1 volt per meter, measured at 1 mile on the on-course portion of the range, which, incidentally, is the area of weakest radiated power. The strength of this field is so low that it has been compared to the power of a fly. So far as could be determined, this localizer was the only transmitter that was operating at Lakehurst at the time in question. It is not believed that other high-frequency stations, at some distance from the field, could have had inductive effect upon the airship. Witness Diekmann of the German Commission stated that he and his colleagues had been particularly interested in the possibility of ignition through high-frequency radio induction, especially after hearing the testimony of witness Freund, who was engaged in paying out a length of the stern cable at ring 47 when the accident took place, that this part of the cable might have received impulses and thus electrical energy would have been conveyed into the inside of the ship. However, it appears that if such result was to occur due to inductive effect, a transmitter relatively close to the ship and of considerable power would have had to be operating at the time of the event. These conditions were not present. Resonance effect due to high-frequency generation within the ship was impossible because all the ship's transmitters had been shut down before the appearance of fire. Furthermore, once inside the ship in the form of oscillations in the structure, no damage could have been done because the structure itself was so large and so complex that there was no possibility of a small amount of energy setting the whole ship in oscillation, and that oscillation in separate parts, which perhaps contained high resistance, would be short-circuited by other parts of the ship. In view of the facts and the expert testimony given on this possibility, it may be said that in such inductance there was only the remotest chance that it was responsible for the elusive spark. Electrostatics. Under this designation of electrical possibilities, there is now to be considered a group distinguishable from current electricity and known as electrostatics. In this group, there is first mentioned a possibility due to the nature of the materials employed. In the older type of cell fabric, containing a rubberized element, it was apparently possible to create a static spark by tearing the fabric. The cell fabric used in the Hindenburg, as far as we could learn, did not include material possessing this characteristic. Since virtually all of the cells were consumed by the fire, no test could be made of the cell fabric. The two bungees in the stern of the ship, connected to the horizontal members of the tail, contained some rubber, but as far as we know, the bungees had not been damaged until after the fire had broken out. Before proceeding further with the subject of electrostatics, It is to be remarked that an airship, as a body, is regarded as carrying an electric charge, the nature and extent of which depend upon the circumstances. In motion, it may accumulate a charge either through friction with the air, or perhaps by means of charged water drops, such as may be found in clouds or mist. It may accumulate a charge of either positive or negative sign. Thunderclouds may carry a positive or a negative sign. According to the evidence in this instance, the ship is assumed to have carried a positive charge on its outer surface, which is a semiconductor. This phenomenon is due to the fact that an airship in flight is within the atmosphere, which is electrified. A few of the more interesting features of this phenomenon are that the Earth ordinarily is charged negatively, that in the atmosphere there is an electrical field measured in volts per meter, potential gradient, which in fine weather amounts to 100 volts per meter, becoming higher as the weather grows more disturbed, that the tendency is for an equalization current to pass from the atmosphere to the ground, that the electrical conductivity of the atmosphere is greater when the atmosphere is humid. Other facts and assumptions are that the total outer surface of the ship has a uniform potential, that the electrostatic effects on the outside of the ship are separate and apart from those on the inside, that a number of conditions tend to equalize the potential of the ship with the surrounding atmosphere. Among these is the dissipation created by the exhaust gases and by the movement of propellers, the edges of the latter being metallically connected with the ship's structure, that the landing ropes would serve as conductors of the ship's charge and equalize the potential of the ship with that of the ground. When the ship is held by the landing ropes, the electrostatic picture is such that the surface of the ship, after a brief interval, so to speak, becomes a piece of the ground elevated into the atmosphere. The potential differences measured vertically to the earth are called the potential gradient. This gradient is higher over those areas of the ship where the edges or points project into the atmosphere, especially over the bow and stern of the ship. It may be increased in the presence of charged clouds. The principal protection against an electrostatic discharge which might serve to ignite an inflammable mixture in or about the ship is the bonding of the ship. Briefly, such bonding is the connecting up of the many parts of the ship so that electrically it becomes one complete metallic whole. A possible test of the state of this bonding could have been made by detecting through the radio receivers the characteristic noise associated with interference created by imperfect bonding. In the present instance, as has been noted, the receiving system of the ship did not give indication that any injury had occurred to the ship's bonding prior to the accident. We have also considered the possibility that, due to a discharge between parts of the ship having different potentials, a spark might have been created. Whether such a discharge occurred, we cannot say. According to the testimony, the ship was bonded in keeping with the best known practice. There was one fixture of the ship in this respect that received more than passing notice: the unbonded electric wires at the stern electric lamp of the airship. Witness Diekman indicated that there might have been a static charge produced by this tail light wiring at the light bulb, since the wiring within it was the only part of the ship which did not have the same potential as the remaining surface of the ship. A very small difference, however. Whether such a small electrostatic capacity as the lamp terminal would have been able to produce a spark is highly questionable. Another reason to regard it as improbable is that no one reported having seen the origin of the fire at the extreme rear end of the ship. Ball lightning. A reading of the record reveals that some space is given to another manifestation of electrostatic discharge, namely, to the possibility that ball lightning might have accounted for the ignition of the mixture. Ball lightning is supposed to be one of the peculiar species of lightning discharges that have been observed from time to time. One of its features is that, like a drop of oil on water, it spreads and splits into segments, some of which segments continue for a distance along objects on which they alight. Although some authorities have disclaimed the existence of ball lightning, we have considered the idea for what it might be worth. It does not very well explain the slow burning that some of the witnesses describe as having taken place at the beginning of the action. Moreover, the theory as applied in the present instance would appear to have little substance, since no one testified to having observed any form of lightning. For the same reason, any other claim made on the ground of lightning as a cause would also seem to fail, because none of the witnesses who testified stated that they observed any lightning flashes in the vicinity of the ship or heard an accompanying clap of thunder at the time of the accident. Brush discharge, or St. Elmo's fire. In order to develop the next possibility to be considered, viz., ignition due to brush discharge or St. Elmo's fire, a few additional remarks are necessary upon the subject of electrostatics and the conditions that actually prevailed at the time and place of the accident. It will be recalled that the bow port trail ropes first made contact with the extremely wet ground 4 minutes before the fire. When they left the ship they appeared to be quite dry, as dust was observed to fly from them as they descended. These ropes were made of hemp. The atmosphere at the time and place of landing was humid, and the ship had absorbed moisture. It was therefore reasonable to suppose that in the interval the ropes continued to absorb moisture and their conductive qualities increased. Therefore, their contact with the ground under the circumstances would discharge the static accumulated on the ship. Laboratory tests were made by the National Bureau of Standards of the electrical conductivity at various humidities of a section of the bow port trail rope to determine whether the static discharge accumulated by the airship was or was not discharged when such rope made contact with the ground. Under the varying conditions employed in the tests, it was found that the airship would be 90% discharged in a period of from 0.6 seconds to 170 seconds after such rope came in contact with the ground. With respect to the potential gradient existing in the atmosphere in which the ship was standing, witness F. W. Reichelderfer, Navy aerologist, indicated that conditions were favorable to a steep potential gradient due to the existence of a thunderstorm condition. Witness Eckener also believed that a high potential gradient existed at the time and place of the accident. He apparently based his opinion upon the following: that a thunderstorm front had just passed over the station, that the heavy rain had become a light drizzle, thus reducing the potential gradient materially, and that from his information the appearance of the sky showed a light stratus ceiling. He proceeded to say that if one closely examined the current registrations of winds, temperatures, and pressures, then one might recognize that the first thunder front must have had a smaller, lighter one following it, that the wind turned back to the southeast. Winds of the higher altitude remained westerly. The barometer curve showed a slight falling off of pressure, and relatively the temperature started to rise again. That is, after the temperature had been brought down appreciably by the breaking in of the cold air, the temperature remained constant for 1/2 hour before the landing maneuver to 1/2 hour after the landing maneuver. Then the temperature again started to decline rapidly, and the wind slowly turned back to the northwest. This, according to the witness, the sensitive instruments show, and that if this was not noticed at the field, it was quite natural, because attention was focused on the landing maneuver and on the handling of the ship. He stated confidently that there was a small tail end to the first thunderstorm that passed by, which most likely created a steeper potential gradient than would otherwise be expected. Whether this stronger gradient could have generated sufficient potential between the airship and the air masses above the ship so that an equalization of the gradient took place, either by St. Elmo's fire or by a spark, he was unable to decide. That the ignition was not effected by such a static equalization spark immediately after the landing lines had been dropped was because they then were dry, hence poor conductors. They slowly became damp in the light drizzle that was falling, and in such condition their conductivity became greater. Therefore, he believed that the potential between the ship and the ground was slowly equalized, and afterwards the potential gradient between the ship and the overlying airspace was sufficient to generate these static sparks. Witness Whitehead, in commenting upon these views respecting the potential gradient, said that if a secondary storm was present in sufficient intensity to cause a spark of lightning of any character, that it would have been visible or audible. At any rate, it would be reasonable to suppose that, probably because of the preceding thunderstorm, the potential gradient at the time and place of the accident was somewhat greater than normal. Witness F. A. L. Darch, aerologist at the Naval Air Station, appeared to have a somewhat different opinion. He stated that previous to the landing there had been heavy showers which could have produced a strong potential gradient, but whether that still existed at the time of the accident, when only a light rain was falling with just the clouds above, he could not definitely say. He did not believe that the potential gradient then existing was dangerous to the ship, but he had no way of verifying his view. In answer to the question, after the thunderstorm had disappeared and the wind and rain had decreased, were there any signs or indications of a new small depression or squall? Witness Darch said that the only indications they had had was the temporary shift from southeast to southwest with the slight, about 1/100th of an inch, rise in pressure. However, no distinctive clouds of precipitation occurred with this change. Brush discharge ordinarily is seen only after dark. It is manifested particularly from sharp points or projections of any material object that is charged to a sufficiently high electrostatic potential so that the charge dissipates. The effect is produced by particles of the material substance or by ionization of the gases of the atmosphere from impacts or stress. The ignition of a combustible mixture of gases in such a discharge is due to transformation of kinetic energy into heat from impacts of ions or particles. The brush discharge appears either reddish or bluish, depending upon the electrical sign of the charge. During the course of the public hearings, the question of whether a brush discharge would produce sufficient heat to ignite an inflammable hydrogen-air mixture was dwelt upon to a considerable extent. Since that time, further experiments have been made in the high-voltage laboratory of the National Bureau of Standards, and it has been found possible to ignite hydrogen by a brush discharge by using somewhat more intense discharges than those previously tried with a somewhat slower velocity of the gas passing the needle point. In this consideration of the possibility of brush discharge, it is to be noted that no witness testified that a visible indication of it was present. This, however, may be accounted for by the fact that darkness had not yet fallen at the time of the accident. Witness Whitehead was of the opinion that the continuous presence of brush discharge sufficient to cause the ignition would require a greater current intensity than could have been possible through a dry rope. Another argument against the brush discharge theory advanced by Witness Whitehead was that there was much evidence that the first sign of fire was through the translucent skin at the point well away from the tip of the fin. Witness Diekmann, in elaborating on this phenomenon, stated that a 1/100th or 1,000th part of a watt, perhaps less, was all that would be necessary to ignite a mixture of air and hydrogen, that it was difficult for him to believe that brush discharge was responsible for the ignition, that none of the witnesses testified to its presence. He remarked upon the testimony as to the presence of glowing reflections of fire which had moved from the stern forward, but stated that such references to reflections were peculiarly indefinite and uncertain. Of related interest to brush discharge was the opinion of Witness Earl that in an atmosphere of high humidity static electricity could be attracted to the top points of the ship when the ship's mooring ropes came into contact with the ground sufficient to cause a spark to jump across the mixture of hydrogen and air, saying that such would be possible if the ship was in relatively slow motion while gas was being valved placing a layer of gas between the ship and the damp atmosphere. The concentrated atmosphere between the cloud and the ship would reduce resistance to sparking, and if the potential of the ship was the same as that of the ground, there would be a possibility of sparking across. That it is easier to spark through hydrogen than through air. The meteorological records and related data of the investigation were made available to Dr. W. J. Humphreys of the United States Weather Bureau. He has concluded, after making a study of such material, that a brush discharge, or several of them, very well might have occurred on the ship after, not before, the landing ropes came into contact with the ground. That this brush discharge would have continued for some time. That it would have been invisible, being in daylight. That such a discharge likely would have ignited any adequately rich stream of leaking hydrogen that reached it, and that from the point of ignition the flame would have shot back to the leak. There quickly would have burnt a larger opening and set going a conflagration of great violence and rapidity. Conclusion. The cause of the accident was the ignition of a mixture of free hydrogen and air. Based upon the evidence, a leak at or in the vicinity of cell 4 and 5 caused a combustible mixture of hydrogen and air to form in the upper stern part of the ship in considerable quantity. The first appearance of an open flame was on the top of the ship and a relatively short distance forward of the upper vertical fin. The theory that a brush discharge ignited such mixture appears most probable. Respectfully submitted, South Trimble, Jr., Solicitor; R. W. Schroeder, Assistant Director, Bureau of Air Commerce; and Dennis Mulligan, Chief Regulation and Enforcement Division, Bureau of Air Commerce. Approved, Daniel C. Roper, Secretary of Commerce. End of Part 5. Appendices of Report of Airship Hindenburg Accident Investigation by the United States Department of Commerce. This is a LibriVox recording. All LibriVox recordings are in the public domain. Appendix 1. Note: Asterisk indicates those who died in accident. Officers and crew on board the airship Hindenburg on its departure from Frankfurt am Main, Germany, on May 3, 1937, were as follows: Captain Ernst Lehmann, died. Captain Max Pruss, commanding, survived. Watch officers: Albert Samt, survived. Heinrich Bauer, survived. Walter Ziegler, survived. Navigators: Max Zabel, survived. Franz Herzog, survived. Christian Nielsen, survived. Kurt Bauer, survived. Radio officers: Willy Speck, Chief Radio Operator, died. Herbert Dova, survived. Franz Eichelmann, died. Egon Schweikhardt, survived. Engineering officers: Rudolf Sauter, chief engineer, survived. Eugene Schäuble, survived. Wilhelm Dimmler, died. Elevator men: Ludwig Felber, died. Ernst Heuschel, died. Eduard Boetius, survived. Helmsman: Alfred Bernhard, died. Helmut Loy, survived. Kurt Schoenherr, survived. Electricians: Philipp Lenz, chief electrician, survived. Josef Liebrecht, survived. Ernst Schlapp, died. Mechanics: Walter Bahnholzer, died. Eugen Benteler, survived. Rudi Bielas, died. August Deutscheler, survived. Jonny Döflein, survived. Adolf Fischer, survived. Albert Holderried, died. Richard Kolmer, survived. Robert Moser, died. Alois Reichsacher, died. Theodor Ritter, survived. Raphael Schredler, survived. Willi Schiff, died. Josef Schreibmüller, died. Wilhelm Stieb, survived. Alfred Stöckle, died. German Zettel, survived. Riggers: Ludwig Knorr, chief rigger, died. Hans Freund, survived. Erich Spiel, died. Stewards: Heinrich Kübis, survived. Wilhelm Baller, survived. Fritz Dieg, survived. Max Hennenberg, survived. Severin Klein, survived. Eugen Nunenmacher, survived. Max Schulze, died. Frau Imhoff, stewardess, died. Dr. Reutiger, ship's doctor, survived. Cooks: Xavier Meyer, chief cook, survived. Richard Müller, died. Alfred Stöffler, survived. Alfred Grötzinger, survived. Fritz Flaccus, died. Werner Franz, mess boy, survived. Observer, Captain Anton Wittemann, survived. Appendix 2. Passengers on board the airship Hindenburg on its departure from Frankfurt am Main, Germany, on May 3, 1937, were as follows: Adelt Gertrude, Berlin, Germany, survived. Adelt Leonhard, Berlin, Germany, survived. Anders Ernst Rudolf, Dresden, Germany, died. Balin Peter, Washington, D.C., survived. Brink Berger, died. Clemens Karl Otto, Bonn, Germany, survived. Dana Hermann, Mexico City, Mexico, died. Dana Irina, Mexico City, Mexico, died. Dana Matilda, Mexico City, Mexico, survived. Dana Walter, Mexico City, Mexico, survived. Dana Werner, Mexico City, Mexico, survived. Dolan Curtis, France, died. Douglas Edward, New York, died. Erdmann Fritz, died. Ernst Elsa, Hamburg, Germany, survived. Ernst Otto C., Hamburg, Germany, died. Feibusch Moritz, Lincoln, Nebraska, died. Grant George, London, England, survived. Heidenstam Rudolf von, survived. Hirschfeld George, Bremen, Germany, survived. Hinkelbein Klaus, survived. Kleeman Marie, survived. Knucher Erich, Zeulenroda, Germany, died. Leuchtenberg William, New York, survived. Mangone Philip, survived. Mather Margaret, survived. Morris Nelson, survived. O'Loughlin Herbert, survived. Osborne Clifford, Chicago, USA, survived. Panis Emma, New York, died. Panis John, New York, died. Reichhold Otto, Vienna, Austria, died. Spee Joseph, survived. Stöckle Emil, survived. Vinholt Hans, Copenhagen, Denmark, survived. Witt, Hans. Survived. End of appendices. End of report of the Airship Hindenburg accident investigation by the United States Department of Commerce. Recording by Scott Danneker, Elizabeth City, North Carolina. www.zeppelfart.com